So right here is where we are in kind of like in the middle of in the US, in the South. My group, a lot of similarities to Arnold's group in a sense that we have, a lot of different backgrounds. So we have architecture engineers and civil engineers. That's the department we're in. But there's a lot of folks coming in from mechanical, computer engineering, CS. I had applied mathematicians, and then also architects. And so that shows, that we're looking into, or the reason behind that is that I want to have a diverse group in order to address the problems of climate change, energy use, energy intensity in buildings more holistically. So you have views from all these different people, while at the same time we're focusing on the computational aspects, but you can't neglect everything else around it. So you don't solve issues in a vacuum. In a nutshell, what we do, and this is the most text you'll see today, I promise, but I wanted to put it out there. We're moving science engineering education in the energy infrastructure, and the two focuses we have is to make that infrastructure human responsive, because that's ultimately what we make it, and intelligent, which is how we make smart decisions as we move forward. Also, we do work on some theoretical aspects, but today I will mostly talk about the applications, because in this context, in this framework, it's a lot easier to show results and some cool numbers than equations and derivations. So sit back and relax and enjoy. Here's a little bit, one way to classify our work. So we work on all the three branches of machine learning, if you so wish, supervised learning. Here we're working on sort of like a one-stop solution that you would take an image from Google Maps and then get out the energy use of one particular building on that map. And so this entails a lot of things like speeding up computations, doing some image analysis, trying to understand the urban context around that building that you're looking at. And then also just making sure that the computation of the energy use that you get out of that makes sense. So that's pretty cool. I think in our first run, we achieved the speed and the computation is about 2,000-fold faster than what you would get when you reference programs. And so we're confident we can make that like a real-time energy use. You can do large cities quickly and retrofit or build or analyze retrofit scenarios relatively quickly within some error bounds, of course. For the unsupervised methods, there's a lot of clustering that everybody's doing, so we're doing also some as well. But some cool things that we also try to do, where I think we're pretty unique, is to try to come up with different ways of clustering systems. So one of our algorithms, we take time series, turn them into images, then do autoencoders on those images, and then we look at what we found in the latent space, and then we turn those back into the time series space. And so this way we can kind of create a nonlinear clustering and pick up signals in different locations on the time series, rather than saying, okay, my feature is, the hour 1 and then hour 2 or whatever. And so this way you can automatically cluster and extract features. Down here, a lot of system integration, a lot of IoT works. I'll show this one a little bit later. My group is also collecting data around the COVID response of the civil infrastructure here in Austin. So we have transportation data, people mobility, energy use in buildings, occupancy in the UT campus, air movements and things like that. This graph here that you see is the average transportation, the car movement around the city. So this is where we had the lockdown drop about 80%, and now it's going up again. So anyway, these are the kind of things that we do. But today, like I mentioned, I want to focus on the RL part, the reinforcement learning part, for two reasons. These are the two big directions that I'm generally focusing on. And also, these are the two grand challenges that I think, folks who work in the built environment or energy issues in the built environment are addressing. And these are basically at the two ends of scale. One, when you come to a building and you're looking at it on the zone level. So you're looking at people and how they perceive a space and how they interact with the space, how we condition the space, and then how we can make that space more comfortable in a more automated way, and also save energy. So putting the occupant into the center of building control, so to speak. And then the other one is when you go at the total other end of the scale, when you zoom out and you start looking at you know, multiple buildings and how they can coordinate with each other and coordinate their response to the grid with each other. And that is because more and more we will see, obviously we electrify everything, we move away from gas and oil for heating and cooling. And so everything will be electric. We integrate renewables, we integrate electric vehicles, batteries, and so on. And so once you have that, you create energy flexibility as asset into the buildings, and using that flexibility, using that asset as a flexible source or a flexible asset is something that grid operators will actually pay money for, but it has to be done in a way that it's not impacting energy use for the individual. So there is a link between the two. But there's also a larger image here, a larger picture. And so you know, you don't have to take my word for it, and I will not show you like how many percentage of energy use is in buildings and so on, but just suffice to say, EPC's program, IEA's EPC program, the Energy in Buildings and Communities program, has recently launched these two annexes which deal with the big questions. And so 79 is the one that started a year ago, where we have a leadership role to demonstrate occupancy-centric building design and operation. My group is part of organizing real building implementations and demonstrating case studies. And then Annex 81, which is launched a few weeks ago, in fact, during COVID, I think in April was the first like real workshop. Data-driven smart buildings, again, the idea that you have buildings, there is data, we have to make smart decisions, or we have to make decisions that are smart and some context, and the context is the grid interactive energy efficient buildings. One thing that's not in here, the DOE, the Department of Energy, is preparing a big call for grid interactive energy efficient buildings. Sorry for repeating the names. But that is organized across the 4 different offices, so the Building Technology Office, Electric Vehicles Office, the Grid Office, as well as the Solar Technology Office. And so those 4, again, demonstrating that this is where everything's going. And so all the big labs are ramping up and then preparing for demonstrators, as are we. And so this is all very timely and are very forward looking. The method by which my group's analyzing all of this is RL, and I will not show more equations. We'll skip all the technical stuff, but suffice to say, the reason I like to work with RL is because you have this opportunity to work model-free and completely data-driven, which is good in a sense that you don't have to generate, you know, models for every single building, so you can be very scalable. And the drawback is that you don't have models, which means you cannot generate things like safety bounds or forecasts and things like that. And so it's like in between this tension of creating super accurate systems that are very good at controlling energy versus more sort of like natural, organically evolving and adapting over time. And I think this approach is more useful for the built environment, because in, you know, the built environment or buildings and systems in the built environment are not like robots. You don't build them and then replicate. You have different types of buildings. You have, even in the same type of building, you have different people. And so you need the system to be able to be adaptive, and people are not robots, right? And so you need systems that can work with and evolve with the people. Okay, I'll skip the technical details. Like I said, you can read all the papers if you want. We have a really nice review paper on demand response using reinforcement learning that summarizes all of that. And so we'll skip to the 2 projects right now. So like I said, the first one on OCC, occupant-centered control. The goal here, and you know, like I said before, we're balancing occupant comfort and energy use, and the way we do it is using adaptive set points. So to give you an idea where most people that do similar work like this are, here's a scale of, a chart of 2 scales. So one, on the vertical axis, you see the number of zones that people are usually analyzing, meaning, you know, 1 meaning I'm looking at 1 office, and then the number of duration of experiments people are doing. And so what you see is most experiments are in this kind of range here. So short experiments in small number of zones are pretty much the norm. This review that we wrote explicitly looked at experimental work, not simulation work, because simulation work is a lot easier than real experiments. And so, but you can tell that, you know, 2-3 months is the highest that people do. 1, 2, 3, 4, 5 offices is usually what's been done. And so that's not really compelling to demonstrate something that is, you know, impactful at scale. So we have targeted this range here where we would have many offices or many zones over a long time period where we would do this. And the idea was, you know, this is one of our office buildings. This is a quarter of the office you see. So here's a perimeter. Here's a perimeter that you can see. This is 1/4, so you know it goes in all 4 directions. We would deploy our IoT devices, and the buttons you see on these are supposed to provide feedback. And the feedback is basically I'm cold or I'm hot. And the reason we use this, and you know, we measure all kinds of different signals just to be able to correlate there's temperature, humidity, lighting, CO2, PM, TVOCs, and whatnot. And so the reason really we create these 2 buttons is to create a simple mechanism. I didn't want to use an app. We also have an app where we can ask for feedback, but it just seems too cumbersome to create that. By the way, the annex research, one of the tasks in the annex work, other people work looking at this exact occupant building interfaces and how you design them more efficiently. And so that's kind of like part of that. But the idea was you just give a simple feedback. It's cold, it's hot, that's it. And then we can take that information, process it. Our infrastructure processes it on the cloud. And then we move and we integrate facility management. This is also a big step that not many people are doing because it's very hard. It took us quite a long time to get an approval and get an understanding of integration, interaction, and what we actually wanted to do. What we're doing is a change of set points of the thermostat, right? So the heating and the cooling set point moving up and down as we want them. But obviously the people that are maintaining the building don't want to start receiving calls from the people in the building saying it's too hot, it's too cold, what are you doing, change this, I'm not comfortable, and so on. So we have to do it very carefully. So that includes things like we can't change a lot at once. That includes things like we can't change things on their own. So everything we do, we try to okay through facility management or utilities. And then, you know, we apply them. And so it sounds negative, but you know, it's hard to work with the facilities, but in fact, it's actually very easy and they're welcoming. They just want to make sure it's not, you know, we don't do something where a whole building explodes. In fact, because, you know, the final frontier in buildings, you know, we understand everything about the systems pretty much. We can control them really well. The final part within a building is the occupant, and there's a huge potential to save energy. And so that's why they're interested in doing that. So this was the plan. We built about 40 of these babies over the past years. And then, you know, this happened, and like literally a week after we deployed in the offices, we had to shut down. I mean, not the university has shut down. The devices are still in there, in fact, and monitoring and measuring. There's nobody in there to give any feedback. So unfortunately, we had to go back and restore to simulation models. But even with these, what we tried to do is we tried to put a little bit of advance, and by advance I mean things like we looked at, you know, a more realistic occupancy model. When are people in the building, which is different from what the Energy Plus standard is, like 9 to 5 without our break. It's more stochastic. And then also a more recent thermal vote model, which is what you see at the bottom here, which creates a probabilistic model of, you know, temperature versus how probable it is that you're going to start to complain. And so we built that, and the next step then is we built it into Energy Plus, which is, instead of doing it as a co-simulation platform, because this way you can again scale it across other buildings and other applications rather than having to recreate the co-simulation, which almost never works outside of your own computer. So this way it's just a file that literally runs natively in Energy Plus, and you can run it in other buildings. the algorithm is the same. And so we picked Chicago as an area, as a place to study it, because the thermal vote models that our colleagues have done come from Canada. And so we're closer to a colder climate. Very important, what you'll see now, Al, in a minute, is that, you know, we randomly initialize the controller. So at the beginning, the controller doesn't really know what it should be doing. And what it does is literally just moving these set points up and down and see what happens the next day. And so I'll show you the results. Again, I'll skip the technical details, but you'll see the results. You'll see here a chart that will move to the right as we move forward in the year. You only see the first 3 months for now, so you can take a look at what's happening. So first of all, you'll see this is a scale from 0 to 1. And so for every day, you basically see a number for each of the 3 possibilities, whether what fraction of time of the occupied time was in the cold area, in the comfort zone, or in the hot zone. So this blue square or rectangle that I charted basically means that for almost all the time, the person was in the hot area, because it's orange, and then it was a little bit of a time in the cold and the comfort, and the same amount of time in the comfort area. So the top one is the HVACLearn, that with the adaptive set points, it's our controller, and the bottom one is the reference controller, which is a typical standard setting following the ASHRAE guidelines of, I have the Fahrenheit number, 7074 Fahrenheit, or 2022 C set points. And so what you can see and so the controller, the HVACLearn in the beginning here doesn't know anything. It's totally random, and so it starts learning as you move forward. And so you can tell, when we're starting to become into the summer, that you see a lot more green here. So most of the occupied time is comfortable, whereas you can tell the reference controller, people are hot. And as you move forward, this is the fall, even more green, nothing really changed here. And by the end of the year, if you look back onto the year, remember, you learn over time, right? So you start here with 0 knowledge, and then you have here, I won't say 100% knowledge, but more knowledge. And so basically at this point, you would start over, go again for the next year, and this first part here would essentially be a lot more greener, because the climate here and here is pretty much the same. Whereas the other one, the reference one, basically it would not do anything. You just start over again and be in this uncomfortable position. You see, I'm comfortable. If you look at this, very little along the years. And so this shows, and of course, this is, I don't want to say preliminary. We did a lot of work on this, but this is one climate zone with this one model. I really, really wish we had experimental work at this point, but we'll do that once we get there, because this slide, proven experimentally, is what's really interesting. Now, the big question, so yeah, we move the set point, we provide comfort. The big question after that is, do we actually save energy? And so I can report that yes, we actually also saved energy on top of that. So the slides that you see here are the energy distribution over 20 times simulating the experiments. You have 20, kind of like a Monte Carlo a little bit. And so the reference, you see, it's very small distribution because it's very deterministic. The set points don't really change, whereas for HVACLearn, the set points move and change. And so on average, if you look somewhat where the average is, you have at least 5 to 10% energy savings that you get for free. This isn't really for free, because nobody really does anything other than trying to understand, trying to make the person comfortable leads to save energy. And that's kind of like a big deal. And so it's, again, for free and scalable, because you can run this in every office. There's not much computing involved other than an update of a table. It could literally run on a Raspberry Pi, but also on the BMS system. So this is pretty cool. If you're interested in more on this, June will be defending on June 16th. June is the first name, but also June 16th will be his PhD defense. If you're interested, I will announce it via Zoom. I'll send for sure Eleni a link, and then you're welcome to, Zoom in at that point. All of this work that I'm showing you right now is also not published yet, so please don't go and copy it. But anyway, if you're interested in this particular work, June 16th, you'll see more technical details behind it and more, more simulations and more bigger pictures, if you so will. Okay, so I will switch to the other project now, the CityLearn approach, when we zoom out and go to the larger scale and talk about grid interactive energy efficient buildings. A lot of the work that we've done here is preliminary in the sense that we built a framework. So we created this CityLearn environment over the past, year and a half or so, which is an open AI gym environment. And so if you're doing research in RL, these gym environments are created so that people can test their algorithms on the same environment, so you can benchmark. But none of such a thing existed for building energy performance. Nonetheless, for an integrated systems with many energy systems, and even less for like a microgrid type situation where you'd have multiple buildings, where you would be able to coordinate the response together. And so this is why we did it. You see over the years, we had a number of publications on these. It's last fall in BuildSys, this is where we officially said, okay, here is version 1, go to GitHub, download it, or citylearn.net, which will link to GitHub, download it and use it. So this is where I will go now. I want to give you this ahead of time so you know what the whole thing is about, where we're going. If you take a step back, we did some review, lit review, to understand, what really the problem is. And I told you the problem, but here's how you can see what the problem is. So if you look at RL for demand response, which is when you create energy systems that are responsive to the grid, first of all, there is a big explosion of publications. As you can tell, sometime here, this is fueled by, the development of the deep neural networks, which made computational easy. Also, you've seen AlphaGo and DeepMind's work. And so all of those led to kind of like an explosion in many different areas. You see HVAC has been always around, but then electric vehicles started to come around. Here are the orange ones, quite a bit. Storage and decentralized generation, so PV systems and batteries. And then appliances on top of it, which is kind of like scheduling problems when you run your dishwasher, washing machine, and so on. And if you look at it only on the left side, you could say, well, okay, we learned a lot. And so now we probably can converge into something. But then if you start digging into the actual methods, and that's what we did in the paper, you'll see that everybody, and well, not everybody, but there's a huge disparity of how people address these problems. So, you see the chart on the right, we tried to kind of, give sense to it. So you can even see at the bottom, at the bottom you have, demand independent prices in your system. At the top, demand dependent prices. So when you're using more energy, you pay more. So that's a big difference to demand independent pricing. And so that those two things cannot be compared with the methods you use. Then whether you use single agents, you can decide or think about, if you have one agent that controls everything, that doesn't mean that you cannot have multiple energy systems. It just means that one agent knows everything. But that agent that knows everything might be different from a lot of independent agents, which again is different from many, many agents that somewhat cooperate or not. And so all of these different things make it really hard to actually make push in this area. And if you also look at what the areas are, in the left-hand side here, the number of papers that address the parts that are interesting to us here, so a multi-agent approach with demand-dependent prices, integrating renewable systems, is really low. And that's the one that we're interested in the built environment, because that we need multiple buildings, we need demand-dependent pricing, because that is how usually it's done, especially when you start doing demand response situations. And then renewable integration, because that is where everything's going. We start to get more and more decentralized, batteries, PV, EV, and so on. And so this is really a big need to create something that people can study it. And so this is why we created a first version of CityLearn, which lets you essentially abstract out. So we abstracted out the buildings, we created the energy demand, we created the systems. And so what you can do now is use the algorithms, run the algorithms in this framework, and benchmark it against other algorithms. And so this way you can really standardize the development, you can push development, you can understand what parts of algorithms or how you have to set up algorithms to make it useful in this world. And specifically, if you know the problem that you're solving is, or we're applying, is energy storage control. So if you have, or assuming you have certain buffering devices, like whether it's chilled and domestic hot water, which is what we use here, or electric vehicles or electric batteries, which is what we don't have yet, but what we're working on now. When you charge and discharge those is essentially the problem that you solve with these. And the other advantage of having it in an AI environment or this gym environment is that all the colleagues in the CS departments are working in this area or in this environment, and they're just cranking out algorithms every 6 months, like all the big conferences, like here's a better algorithm, here's a fast algorithm, here's an even more efficient algorithm. And so we, like the first year and a half, we were struggling just to keep up with those algorithms and implementing them. First of all, reading the CS papers is not particularly straightforward. And so if you can pull, you know, from a GitHub that is set up for a gym environment and run it on these buildings, you can immediately see the value of those. So some adjustment later, but you can immediately see the value of those. And so this way we can actually help two fields come together. The building environment, the building field, the energy field will profit tremendously from the algorithms that are developed by the computer science community to see how effective they are in this field. And then the computer science community, in fact, has an environment to study this problem, which is even for, I mean, not even, but you know, creating multiple agents that coordinating a response is not something that has been solved. And so it's an open problem in the CS environment as well. And so it's a mutually benefiting environment that sits in between the two fields and brings everyone together to the same table. We're interested in the district scale load energy management, so to speak. So let me show you a small example from some very recent results. Again, like all of this is unpublished, so we'll have to improve on the results to make them publishable. But you know, you see where we are with this. So here's an example of 3 buildings, multifamily. Again, we have storage of hot water, which is typical, and chilled water, which is not so typical, but it helps for us to work with this. And then air-to-water heat pumps to store energy in those storage tanks. And the second building, we also installed some PV. This just to make it more interesting to see. To give you an idea, so what the data is that it's using. So the algorithm itself, the self-active critic is using. So you have 2 neural networks that are working unisono. We use things like months, day, hour of the day, some environmental data, including some forecasts on solar radiation. So 6, 12, and 24 hours ahead. So that's the only forecast we use for our system state. This particular setup is in New Orleans, so it's a heating climate. 2A, it's hot and humid. Non-shiftable loads are forecast, so that's a demand from the building. If we have PV generation, the current electric consumption, and then the state of the charge for the charging systems, the chilled water tank and the hot water tank. And like I mentioned before, the actions that the controllers can do is to increase or decrease the state of charge. So basically, do we charge more the storage, or do we remove chilled water or domestic hot water from those? And again, what I want to emphasize, you know, there is no physical model development of the building. So you don't know more beyond that system is in the building. We did some sizing ahead of time, so the systems are sized enough. One thing that we'll be doing next is to see what happens when we're undersizing the systems. But for now, we have enough storage and so on, so that we're not running into an issue there. We initialize randomly. And at this point also, we don't exchange necessarily information between the buildings. So one building does not know what the other building will do in the next step. The random initialization part and the no model development part makes it really enticing, because what that means is that every single algorithm starts exactly the same way on every single building. Of course, you know whether or not the building has PV, but that's the only difference that these buildings have. And so this way you start it, and then you adapt over time to a better approach or a better control of your system. Yep. So here is, oh, this is the only formula. I promise no more for that. But just to get you an idea, the reward signal, which is, if you know, from an optimization perspective, that's your objective function. And the way it's put together is also a lot like an objective function here. So you have weights here. So the left one, the left side, which is built to reduce your peaks. So the building energy use and the total energy use of the microgrid. Weighted against reducing the ramping, which is something that you want to avoid, is to have a large steps in energy use from 1 hour to the next hour, or from one 15-minute step to the next 15-minute steps, because that means that eventually, very suddenly, one power plant has to come online. And so you want to avoid that. So these two overall objectives are weighted against each other. Then within this, we also have goals that are attributed to individual buildings. So the energy building of individual, the energy use of individual buildings should be reduced, but also we provide the total energy use to the buildings as an objective that they receive after they have used it. So it's not that they know what they will do, but they will get a feedback what everybody has done afterwards. So again, this whole setup is running somewhere between you know, an optimization, but also like decision making and a little bit of game theory. So what should we do to improve our position for the future? The only difference is, as opposed to like you know, a game theoretical approach where you have opponents, here the energy total of everything needs to go down. So you really only have a social objective, social collective objective to reduce the total energy use, and you know, shift your own use so that everybody's is going down. And so here's some of the results. On the left-hand side, oh, I should have shown them separately. Anyway, so on the left-hand side is a reference controller for all the 3 buildings, and you want to look at the orange curve. The blue curve is if you have 0 storage, so it's kind of like our baseline. And then the orange curves are the ones with controllers. On the left-hand side, the rule-based controller, which is set up for, you know, reducing your energy use. This is what typically your energy person would do in your building, set it up according to normal settings, and then run it. And then on the left-hand side, you see the RL controller and the range that the RL controller goes through over the summer for reference. And what you want to compare is the orange curves. The blue ones are the same on both, but you see on the orange curves on the left-hand side. So let's see here. So here you create these 2 peaks. These are the morning and the evening peak for residential buildings, which are not, you know, that's typical for residential buildings. When you wake up, you start, you know, making breakfast, making I want to say making cookies, but I meant making coffees, and then, you know, you go to work. And then at the evening, you start cooking again, you start ramping up your AC, and then you create a second peak at the evening. And so that's, you know, you want to avoid those peaks. What you want is more of a flat curve that runs more, you know, like this. And so if you look at the right-hand side, you can see that the RL controller pretty much flattens this curve. It also reduces the number of peaks. Well, actually, no, I mean, it reduces this late peak, and this one is still there because that's a morning peak that you cannot really avoid for that. What you also have is that you see that here, these parts are shifted away from here, which means you're shaving off that part of the response that is generated, so that, you know, you pre-cool your building, for example, and then you cool slower during the day, rather than optimizing for energy use when you're in the building, then stopping everything and then ramping up again at the later stage. So like I said, this is pretty cool. Remember, the buildings don't really know anything, so we didn't have to set up a complicated building models, forecast models, optimization models, other than the objective function, which is data that is coming anyway. So it didn't need to do that. There's obviously a lot of some tweaking of hyperparameters that we're currently doing, to understand which results give us the most sort of stable performance. But you know, we're working, and so again, this is something that if you want to hear more, Jose, my other student, will be defending his thesis August 7th in about 2 months. Yeah, and so then you'll see more of these results and also more coordinated responses that we're currently working on. So what if you know one building is doing this? How does that propagate to other buildings, and how does that change their decision making? Which will be looking quite cool, as I can show you right now. These two plots basically show you the demand response metrics compared to RBCs. On the left hand side, you see how your peaks are going down. So one means it's, you know, RL and RBC are the same, and then smaller than 1 means RL is better than RBC. And so you see after one epoch, so after one summer, you're improving everything in every single domain. The daily peak, that's well, it should be the orange curve, it goes down, so you're using the peaks. The load factor is this ratio between peak and average load, which is something you want to maintain constant, so you don't jump around. It's kind of like a capacity factor. If the load factor is very small, it means that you have high peaks and low average load, and so that's not a good way for your power plants. And then ramping, and what I mentioned before is you don't want to have to jump too much between one step and the next one, because that also puts strain on your energy system. And again, after one summer, you see that we have converged to a better solution than the typical solution that you would see in building setup. So again, I will send out the invites to Eleni, and then Eleni can distribute them, and you can sign up or zoom in about 2 months if you're interested in these results. So to summarize, before I give you a quick outlook, but to summarize, the reason I like RL, and then this is you know, cool stuff, and we can discuss all of these, but the model-free approach means that it's cheap computationally. You don't have to sit down 5 engineers to build all the energy systems. Scalable, if you add buildings to this, you don't need to add more variables in a sense that are connected, but you have individual buildings with their same variables. So it doesn't become more complex, it just becomes a lot bigger. So that's pretty cool. The adaptive part means that you can randomly initialize, and that means you can easily deploy across many, many buildings, which is cool because that means you can scale. And that means you have impact at scale. And that means you have impact across many, many buildings, which is what we want, right? The off policy part is a feature that you can learn from past data. So we can actually start with, you've seen that there is the RBC in the beginning performs better because it has some domain knowledge, but over time that's being eclipsed. So you can learn from that. So you can start randomly, you can observe the RBC controller, and then once you know a lot and you're robust and you're confident in your knowledge, you can actually transition to your RL controller. And I haven't shown that, but we've done an experiment like that as well. That, you know, you can start with your RBC values, and once you know your behavior, you can actually then say, well, now I'm good enough, and I'm going to transition and update my set points according to the reinforcement learning control. And then effective or efficient, this is also something that we've done very early on that I haven't shown here, is that shows that once you have more than one energy systems in your building, so like storage and the PV, or storage, EV, you know, and HVAC, the RBC setup becomes really complex, and you have to really go into it and figure it out. And of course, you could do it with MPC, but that has its own issues. However, as soon as you have more than one of these systems, and systems becomes more complex, the RL is a lot more suitable to find much better solutions. So the RBC will get you pretty good, but the RL will improve upon them for free. And that's the whole point, right? I should have put here for free. Yeah, there is one paper, I'm not making this up, but it's for free. There is one paper from a Belgian group that is literally entitled something like X amount of gigawatt savings in building heating for free using RL. And so that's kind of like the idea behind all of these, is that it's almost, you know, I'm not going to say too good to be true, but it's there, right there, that you know, there's a lot of opportunities. Some success stories with CityLearn. You know, we released this in the fall, and then we organized a challenge for people to basically use it, and we are awaiting the last set of submissions, I think June something, 5th or 7th or something like that. So a couple more weeks. We have, I think, 5 groups across the world, which is pretty cool because I haven't known of them that they're interested in this. With some pretty interesting results, and we'll publish on those pretty soon with them and then together. So that's the challenge. If you're interested, again, on citylearn.net, you can read all about it. It's all online now. You can see it. What's also cool is, like I mentioned before, our computer science department actually used CityLearn in their reinforcement learning course, in their base course. So some students who opted for it could use it to set up their RL controllers that they learned about. We have used it in a power system summer school that we were teaching in Melbourne before all the COVID stuff in February. That was fun. And which is what I'm really happy and mostly proud is that we've seen already people starting using it and writing papers with it in the places where I'm interested. So HVACLearn, the learning representation conference, CS people, and then e-energy, which is happening in 2 weeks, have had papers or are having papers using CityLearn and then coordinated response of buildings and analyzing and using it also as just a platform to understand RL in the built environment. 2 calls that I want to drop if you're interested. There is a special issue that I'm organizing based on the CityLearn environment. It's in fall. If you're still itching, if you think you can do it, go ahead and try, and then, you know, come and publish. If you're interested in a more not casual, but a less stressful environment and a journal publication, we are organizing a workshop at BuildSys, which is the premier conference for you know, energy efficient buildings and intelligent buildings. So in the fall, it's supposed to be in Japan, but it's likely going to be online. We just received note last week that RLM 20 will happen, and so Mario and I, Mario from Carnegie Mellon and myself, will be organizing this, and we'll be sending out the call for papers soon. If you're interested in any topic that it's not CityLearn necessarily, but any topic that is touching on, you know, RL in the built environment to some extent, applications, theoretical foundations, or also just ideas. I mean, opportunities and challenges. There's a paper that just came out from LBNL that literally is challenges and opportunities and challenges for RL in the built environment. So if you want a good start for this topic, that's probably a really good paper to read. And then, of course, side-out papers. That's a side note. So one topic, I think Julie mentioned this yesterday in her talk, but I wanted to pick it up for those of you who couldn't make it to her call. Something that you ought to remember, right? We always hear this by 2050 deadline, 2030 is being moved to 2050, and so on. But you got to remember, when you're in the built environment, you know, all the HVAC systems, everything you put in has a lifespan of 20, 25, 30 years, right? Structure even longer. So everything that's embodied, you put in today, the embodied energy stays there for the next 100 years. Every single HVAC system you put in today will be there for the next 25, 30 years. And the reason I'm emphasizing is because Austin here is one of the fastest growing cities. So people are building like crazy nonstop. And so I can see this developing in front of us, which is basically a huge disaster because this is not, you know, addressed appropriately. So one project that we're trying to do, is we need to recognize, right, that intelligent energy management, which is what I've been talking about all this time now, is just one part of this puzzle. We can't, you know, when I just said 25, 30 years, 100 years down the road. So that means immediately, you know, if you're looking at 10 years down the road, the climate will be different. Like there's no question about that. If you go 10 years back, the climate was different. So that is something that we as engineers and also as people researching, you cannot neglect this anymore from calculations, from models, from forecasts, from analysis, from optimizations. This is part of the world now, and we need to include it. So we include that in this particular project. So the forecast scenarios, you see here the temperature and 3 different climate forecasts for Austin. Then there's people, right? I say these things like, okay, let's assume there is storage, there is PV, there is HVAC, there is domestic hot water storage and whatnot. But that's not something that just happens overnight. You need policy to put that in place. When you need policy, that there you have technology diffusion that create, you have early adopters and you have mainstream. You can impose things, but all of those will create a different opportunity of how you implement things over time. If you just let it run free market ways, it will be purely based on economics. If you have some incentives, you start changing it and modifying that. But you need to include that again, because now you're looking at, again, time scales that are now in 5, 10, 15 years. So climate change is impacting this quite a bit. And then lastly, again, if you think of timescales 15, 20, 25, 30 years down the road, the city that you're looking at or the development that you're looking at today will not be the same. There will be more people. Some places will have gone from residential to commercial or back, or have merged with other places. There will be new roads, bigger buildings. And so your analysis that you're doing today for a particular part of your neighborhood will not look the same in 20 years. And so assuming that it will and making assumptions based on that is ludicrous. And so all of these need to be integrated into common decision-making framework. And so this is why we put together this, we're working on this project, so we're not putting it together, but we're working on this between, the architecture school, our school, computer science, and the public policy school, to come up with this integrated framework and even just try to understand how things affect each other. I don't think we'll solve this, but trying to raise awareness that one thing will affect each other, and in a complex system way, small changes in one hand could have devastating effects on the other hand, climate change being one of them. We're trying to understand it. So my point is, we can't work in isolation anymore when we're looking at building energy use and urban energy use and the smart buildings and smart cities kind of environments. So please don't. And so, yeah, that's kind of like the idea. As we move forward, things change over time, more systems come online, and how we manage this and how we understand what will evolve, how we make effective policies to drive this is in the end what matters. All right, I think I'm right on time, and we have a few minutes for questions. Thank you, everyone. If you have questions and we can answer today, send me an email, go to our website, harass me, follow me on Twitter, whatever.